Hi, this is Greg from Structural Toolkit. In this video we're going through the analysis and design of a multi-span reinforced concrete beam. To analyse and design our concrete beam, we'll be using Structural Toolkit's analysis package to first analyse our beam and then convert it into a concrete linked member design, where we will be using STK's automated concrete design feature to work out our reinforcement along each span. Because of the complexity of concrete design, we won't be going into any detail of the theory behind the various bending, shear and deflection checks themselves in this video. This may be something we'll cover in the future. Along with creating a concrete linked member design, we'll also look at just designing a span without the creation of the linked analysis. At the end, we'll also cover how to manually create and design a concrete beam for users who do not have access to Analysis Standard and have analysed their multi-span beam using Analysis Lite or an external analysis software instead. The beam we will be looking at is a simplified example consisting of two unequal spans, being 6 metres in the left and 4 metres in the right. We'll have a floor dead load of 12 kilonewtons per metre and a live of 24 kilonewtons per metre over both spans. These loads have been chosen to help showcase various design situations. We'll be looking at a beam with a geometry that's 600 deep and 400 wide, and with a concrete strength of 32 MPa. We'll be starting off with setting up our model in Analysis. Have a look at our Analysis Lite and Standard videos if there are any aspects of setting up models you don't understand. To begin with, we'll open up a new blank analysis document. You could alternatively use the wizard feature to set up a multi-span beam, which would also provide a good starting point. We'll just be looking at 1.2 dead load and 1.5 live load in this design example, though in a real design you will need to consider other load combinations, such as 1.35 dead load and partial or pattern loadings as per AS 1170.1 clause 3.3. We'll first draw out our two spans. We'll pin the far left node and provide a roller for the rest. Next we can look at setting our beam section. We'll call it beam and set the material to conc 32. You can create your own material if you want using the Material Properties editor. You can also edit the currently selected material here and, for example, change the density as needed. We'll then set our profile as a rectangle and input our depth of 600 and width of 400. Rotating our model and turning on materials to the left can give us a good visual representation of this. Next we'll create and add our loads. First we'll make our dead load UDL. And then our live load UDL. And finally add each load to their respective cases. Next we can analyse our model, noting that the creep warning, which is advising that the long-term creep effects are not considered in the linear results. Here we can see the moment distribution across our spans. And what we'll be wanting to do now is to perform a design for each of our spans based on these moment diagrams and determine a suitable layout of reinforcement along each span. For users who have access to Analysis Standard and are on a current subscription, we can quite easily convert each span here into a linked member design, which will take our applied loadings within each span and moments at the ends and replicate our results in an analysis document, which will be linked to a concrete member design that also contains the beam geometry and properties we've set in Analysis. This design document then performs an automated design for bending and shear reinforcement based on standard design checks such as moment and shear capacity, minimum RIO and spacing requirements, and also crack control. To get a better idea of what this all means, it will probably be easiest to just go ahead and convert our first span now and see what it looks like in practice. For users who don't have access to this feature and are using Analysis Lite or have analysed their beam using a different software, we'll cover at the end of this video on how to set up a linked analysis to perform the same kind of design. We'll include a timestamp of this below in the description. However, to understand how the automated design works, you'll want to keep watching from here. So to convert our spans, we'll first select the one on the left. Right click, and under Member Design, we get the option to either just convert to a member design, member analysis, or a linked member analysis, which combines both, and will be the option we will be selecting. We'll explain a bit more about the differences between each option later on. Now, these member design and analysis options will only be available if we have a valid beam model, are currently viewing only one load combination, and have analysed our model. You can also convert individual load cases to a design only, but not to any analysis. Now, when we say a valid beam model, for concrete in general terms we mean a 2D spanning beam from support to support. You won't be able to convert a 3D model of any kind. So in our case, we just have our single load combination on, and with our beam already analysed, these options appear. If we were to invalidate our model, we can see the options are now greyed out. So we'll reanalyze our model and select Create Linked Member Analysis. We'll be selecting floor live load. This will affect our psi values, which are used for deflection. This option then relates to the reinforcement termination requirements in AS 3600 section 8.3 and will provide additional result points to help with this. For this video example, we won't be covering the detailing aspect of reinforced concrete members, and so we'll just select no to keep things simple. This next option then relates to the difference in psi values for a concentrated point load and UDL. As we do not have any point loads on our model, it doesn't matter in this example. If you were to have a mix of both, then an approximation is made between the two values. Finally, we have a message about the reinforcement shown not considering the detailing requirements from section 8.3. and then also a conversion complete message. Most of these messages can be set to not show again for subsequent designs to help reduce any repetitiveness of converting members. With our conversion complete, we're brought into the Results tab of the Concrete Member Design module, where we have a completed design for our span. And alongside this, we have a linked analysis document, which has imported all the data from analysis of our left span and uses exact support rotations and moments in the bottom right to match the analysis. Though for our example, this isn't really necessary. We'll touch on this more later. If you wanted, you could edit any of the inputs in here and then redo the automated design. though you will need to remember that your support moments and in some cases rotations may be incorrect. Now, an alternative to this is to convert straight to a design without the linked analysis, which we'll show now. And instead, the results data would be transferred directly into the member design. Generally speaking, the resulting reinforcement designs will be the same either way, but without a linked analysis, some of the functionality of the automated design will be slightly restricted. That being said, for your day-to-day design, you will most likely find that just the design conversion by itself will suffice. We'll talk about any restrictions as we go through how the automated design works. So what we have here is basically an overall summary of the automated design, where each row of the table refers to a design point along our beam span. As default, there is at least 13 points along the beam, with 11 being at equal intervals along the beam and 2 being at a distance of dv in from the support, which is where shear design starts to be considered. Refer to some further information on this in the bottom right in the notes section. Any additional points beyond the initial 13 will be due to options to the right regarding additional design points or locations of point loads on the span, etc. In our case, we have 2 extra points, one for max deflection and one where our moment equals 0. At each point, the bending and shear reinforcement is determined based on the transferred bending and shear force, and also torsion and axial forces and various default settings. Further to the right, we also have the utilization ratio of both the moment and shear design, though noting that within each of these ratios are multiple design checks. So for example, our ratio for moment here isn't just moment capacity, but looks at, say, crack control as well. Finally, at the end, we have comments and errors for each point. We'll see this in action a bit later. Each of these rows are essentially their own individual design and can be edited and viewed by selecting the row and clicking Edit. This will populate the rest of the design tabs of this document with the data of that particular design point. We'll show this in more detail later on. Looking at the other buttons we have to the right, Analysis will take us back to our linked analysis document. Design will perform the automated design with the linked analysis data again. For example, if you had changed some loads in the linked analysis. Clear design clears the current design data. Save point can be used to save edited data. We'll see this more later. Reset point will reset the point currently being edited back to what it originally was. And finally, deflection design will take us to the max deflection and will allow us to view what our deflection will be, like so. Effectively, this is selecting the design point that relates to our max deflection as shown in the description of the row. Now, obviously there could be quite a number of valid reinforcement solutions that will meet the design requirements. To deal with this, we have a set of design parameters that the solution will adhere to in the bottom right. At the top of these options, we have two inputs for additional design points and can help with locating maximum force points and also be used for detailing requirements. Note that changing these will do nothing for designs that do not have a linked analysis attached to them. We then have minimum and maximum bar sizes for tension and compression zones along with bar spacing rounding. Next is then min leak diameter along with spacing rounding. Second to last, we have an option for whether we want to design for cracking or not. So if this option was turned off, the design would not consider any of the cracking requirements. And finally, we have an input that allows us to modify the compression reinforcement used in the calculation of KCS as a percentage of the tension reinforcement. So at 100%, the KCS would go to 0.8, resulting in improved long-term deflection performance in accordance with clause 8.5.3.2. Changing any of these inputs will affect the way the module determines the reinforcement at each point. All these inputs can be used with presets, so you will be able to set your own default values for performing designs. And in a similar sense, if there are inputs on other tabs of the concrete member designs that you want a different default for, such as reinforcement cover, then you can use presets for this as well. Have a look at our useful features video to learn more about how to do this. Now, to see this in action, we'll try changing one of our inputs to see the result in our summary table. At the moment, we can see we have a mix of N16 and N20 bars, being due to the minimum set within our input area for compression and tension. And we can see the bar size transition where the moment sign changes towards the right of our support beam. We also have quite a few changes in bar number. To see if we can get a more uniform bar distribution, we'll try setting both our min bars to N20 and see what happens. With our input changed, we'll press design again. This time around, we only have a few changes in bar number, and with all the bars being N20, we have a quite easy to detail and construct bar layout over our beam. As we explained before, you can also edit points and change the designated reinforcement. For example, if you weren't happy with chosen reinforcement at a specific point, we could select a cell on its row and then click Edit. As an example, we'll change our bottom reinforcement for our second row to be 4 N20s instead. This point is automatically saved when you tab or enter out of the cell. Alternatively, you can just click Save Point. This will then provide us with utilization ratios for this new reinforcement input to the right, along with any relevant errors so we know that we haven't caused any problems. To revert the reinforcement back to the original design, we can then click Reset Point. Now, say we want to know a bit more about why the amount of reinforcement we have here was chosen. For example, we can see our second row here has quite low utilization ratios, so you might think that 3 N20s shouldn't be needed. Changing our bars then to 2 N20s. Instantly we can see to the right that there's a warning. We need additional tension bar area due to our shear design. Although in this case, because the requirements seem so minor, you may just accept this. As we discussed before, at the moment the point that we are editing is currently populating all our design tabs. So if we switch over to the design tab at the bottom, we can see this error in more detail again. Instead of changing the bars in the results tab, you can also change them here while editing. If we switch to the shear tab, we can also see the same error. So now that we know that the reinforcement needs to have 3 N20s, we'll just click Reset Point. The final thing we'll now look at for this span is our deflection. Clicking on Deflection Design brings us to our maximum deflection point, which is also designated by the comment to the right, along with an indication that this point's reinforcement is being used for deflection. We can also see that the right support row is also used as a point for this. These points for reinforcement come from clause 8.5.3.1 of AS3600, whereas we have an external span of a continuous beam, we would take half of the midspan I effective value and half of the right support I effective value. Switching over to the deflection tab, we can see these reinforcement values are already here. We can see above that our total deflection is span on 582, being well within the limits of a typical span on 250. If the deflection did not work, we could look at considering a percentage of our compression steel in the results tab as we explained earlier, or increasing the size of our beam, which we'd need to do in analysis and then convert again. Going back to the results page, for this span what we'll likely specify as reinforcement then is 2 N20 top and 3 N20 bottom along positive bending, For negative bending, we'll then have 3 N20 top and 2 N20 bottom. For our shear reinforcement, there is a short 1200mm long section where ligs are not required, designated by the N12 spacer. However, for simplicity, we would likely adopt N12 at 450 centres along the entire span. There will also need to be consideration of lap lengths and other detailing requirements, such as where the bar numbers change, but this is beyond the scope of this video. Next, we can look at converting our other span, which will be the same process as before. Once again, we'll set our min compression bar to be N20 to be consistent with our other design. And click Design again. We'll then press Deflection Design, which we can see will not be a problem due to the interaction of our adjacent span's force and rotation at the middle support. This time we get 3 N20 bars top and 2 N20 bottom for negative, and then 2 N20 bars top and bottom for positive. For shear reinforcement, we once again have N12 at 450 centres, which we can stop at 1600 from the middle support and use N12 at 900 or something similar that's sufficient to hold the reinforcement together. And with that, our multi-span beam design is done. Now, for users who have not used Analysis Standard to analyze and then convert their beam, what you can do instead is effectively replicate the span's bending and shear forces in a linked analysis, which can then be used to design with. So in simple terms, rather than converting our analysis into a member analysis document, we just set up all these values ourselves. To quickly demonstrate this, we'll replicate what our left span looks like. To start with, we'll open up a concrete design member. And first we'll need to input our geometry and concrete strength, which was 32 MPa, 600 depth and 400 width. Next we'll click Analysis to get a linked member analysis document. Our span is 6 meters. Our span type will be Other, which will allow us to set our support moments. For our dead load, we have 12 kilonewtons per meter, and our live we have 24. Our live load type is floor, so we can leave it as it is. Now for our end moments, if we look back at our analysis, we can see the right support is negative 201.1. So if we put that in, we can approximate our moment diagram. We can see our max positive moment as a result of this is 168.4, which if we look at our analysis again, is slightly different. This is due to the density of concrete in analysis as default being 2500 kilograms per meters cubed, multiplied by gravity of 9.807 meters per second squared, whereas in member analysis, it's just 25 kilonewtons per meters cubed. If you change the gravity in analysis to 10 meters per second squared, you would get the same answer. In our converted span we did at the start of the video, we can see that the conversion just modified the density to make it match. For our example, we'll leave things as they are. Another thing to remember is that for certain span types, such as a cantilever or more complex analysis models with various point loads, you'll need to extract further information from your analysis in order to better match the moment distribution and deflection or rotation of the span. Inputs for this are in the bottom right of the module and can relate to case-specific moments and also rotations at the support where cantilever is used. For our analysis here, we don't need to worry about this due to our uniform loading. So with our linked analysis set up, we can switch back to design Go to our Results tab, set our minimum bar diameter as 20, and then press the Design button. And what we should end up with here is effectively the same design we had with our original conversion, with only some slight force differences. Using the methods shown in this video, you should be able to complete a vast range of concrete beam designs, whether you're using Structural Toolkit's analysis or an external analysis program. That about then covers the basics of using the automated concrete beam design feature of Structural Toolkit. Feel free to check out our website and our other videos for more tutorials and help with using this software. If you have any questions, please contact our support team via email or by calling us. Thanks for watching.